rules, but most.
Yeah, there are rules. There are not many exceptions. Just we have three rules of these sounds. Like lots of letters, but then I pronounce like 2, 3 sounds.
Well, also, some
Okay, let's make a start. So today I wanted to tell you a little bit about the fast Fourier transform, and particularly we'll hopefully finish up at the end of our session today, thinking a little bit about how a data parallel version of that algorithm works. And the most important take-home message is don't try to write your own fast Fourier transform code, because it's a really fairly painful exercise. And so it's one thing, so it's tricky. The bookkeeping is tricky. I mean, algorithmically, it's fairly straightforward, as we'll see. It's quite a nice bit of mathematics that shows how it works. But in terms of translating it into a piece of code, there's a lot of bookkeeping and a lot of places to go wrong. So it's not a terribly fun exercise. I'll try and explain how that bookkeeping works, in case you're tempted to try and write your own. And of course, the main point is there's lots of good libraries. It's such an important algorithm, has such widespread use that a lot of people have spent a lot of time writing very good libraries that are also quite easy to use. I'll show you a little example at the end, hopefully, if it'll compile on my laptop. So two good reasons there. One is it's hard work, so there's the laziness argument, and also two, there's the fact that it's always sort of a solved problem. There's lots of very good libraries. But I think it's worthwhile exercise as HPC experts, understanding a little bit about what goes on inside those libraries, so you can understand how they will interact with your code, how they'll perform, and so on, how to lay out your data in an efficient way, and all those issues. So as an expert on HPC matters, you ought to have been exposed once to the guts of these codes, at least to understand how they work. So the fast Fourier transform, perhaps it's the most important numerical algorithm of all of the 20th century. So about 60 years old now, I say. No, 50 is, yeah, 1965, so I can't do arithmetic today. So devised in 1965, and sort of the algorithm that gets used is attributed to Julian Tukey, who published their paper in 1965. It's based on an older lemma, a sort of central idea, how it works, how it works efficiently. It's based on what's called the Bennigsen-Lanczos lemma. And of course, it has, of course, an older history. That after they published their paper, somebody realized actually that Gauss had invented the fast Fourier transform some hundreds of years earlier, found it in a paper of his studying some astronomical data. So Gauss did everything, of course, and this is not an exception to that rule. So what's the problem we're trying to solve? So we know what the Fourier transform is. Here, of course, we're discussing discrete Fourier transforms. So we're going to take a set of data, a sort of time series of data where something's been sampled at a discrete set of times. The values themselves, of course, can be continuous, but there's a sort of set of sample times. And we'd like to look at the spectrum of that thing in Fourier space, the frequency spectrum of that time history, which again would be another discrete set of values. The allowed frequencies will be sort of quantized essentially. It's a unitary transformation, so of course if we send in n numbers, we'll get n numbers back out of the transform. And the definition of this one given is hopefully familiar to you. Basically, you just sum over all values of x coordinates, multiplied by this phase, which includes this wave number, this frequency k, and that gives you the transformed component f equivalent for that value of k. And then the inverse transform looks exactly the same, except in the phase we have a minus sign. So this very nice algorithm, attributed to Julian Tukey, will compute the Fourier transform in an amount of time proportional to the length of the time history, the vector, the amount of data we have, which scales like n log n. Now, of course, if you look naively at those expressions, the expression that you would use if you just trivially evaluated that sum, then you see there's a sum over n terms, and you have to do that for every frequency. So trivially, if you just naively implement the algorithm and naively compute the Fourier transform, it's an n squared algorithm. So of course, going from n squared to n log n is a huge jump, it's a huge difference. And it means that, if you have a million numbers, you might hope to evaluate using the fast Fourier transform, you would take impossibly many floating point operations to do it efficiently using an n squared algorithm. So the difference between n squared and n log n is enormous. And of course, that's why, basically the entire digital telecommunications era was heralded by the existence of this algorithm, essentially. And it works by a recursion relation, and the recursion relation is encoded in this thing called the Danielson-Lanczos lemma. And for the recursion to work, so here's the first sort of practical point, is that we need to be able to break up this vector into small, the length of the vector needs to factorize. So if n is a prime number, then you are stuck. You can't do it. Fast Fourier transform, this algorithm doesn't work. I mean, you can pad the vector at ends and make it artificially longer, and that would solve your problem. So all is not lost, of course, but basically we're going to make assumptions for the rest of this lecture that we're going to treat n, the length of this vector, as some power of 2, to keep the argument simple. Now, if you go and look at these very nice libraries, they do obviously account for different vector lengths, but they only work effectively when you can break n into small factors. But for today, let's stick with the simple case. You can sort of see how the idea will generalize to arbitrary sort of factors, products of factors. But let's stick with the simple case where our vector length is going to be 2 to some power. And this recursion is basically going to break down n into chunks of 2 and recursively solve this, compute these Fourier modes down in these smaller and smaller chunks. So you can see that obviously that recursion is going to work by factorizing n. So n needs to be able to we need to be able to factorize n. There needs to be an appropriate constraint on a good choice of n. Okay, so it works thanks to this thing, which is called the Danielson-Lanczos lemma. And here it is, and it's the simplest example of it. I'll generalize on the next slide. Let's imagine we wanted to compute the length 4 Fourier transform. It's a fairly trivial task, but it illustrates this point, which is then encoded in this Danielson-Lanczos lemma. So you see, so we've got some data that's in those grey boxes there, some 4 numbers sitting in our computer's memory. We want to compute the Fourier modes, and they're written down in those columns there. Phi twiddle 0, 1, 2, 3 are written out explicitly. And they're just sums with the weight with these phase factors. Since we've just got n equals 4, we just need the phase factors are either plus or minus 1 or plus or minus I. So we just write out those expressions. That's what's in that box. And what we see straight away is that those expressions have some sub-expressions that are common. So in phi twiddle 0, you see that phi 0 and phi 2 appeared in the original data, and they're added, phi 0 plus phi 2. And that same expression appears in phi twiddle 2. So phi 0 is the sort of flat mode where we sum over everything. Phi 2 is the most rapidly oscillating Fourier mode where we go plus 1, minus 1, plus 1, minus 1. But you see that there, that gap of 2, there's a plus 1. So that the sort of sine wave has a peak at both those points. And so the sub-expression is phi 0 plus phi 2 there as well. So in those red boxes, you see those 2 common sub-expressions. And similarly, now if I think of the one unit of one frequency 1 component, then we would have phi 0 plus I, phi 1 minus phi 2 minus phi 3, and the minus 1 component, which is in this phi twiddle 3, is phi 0 minus I, phi 1 minus phi 2. But again, you see there's a common sub-expression if I stare at those 2 expressions, and look at the contributions, the components of phi 0 and phi 2, you again see there's a relative minus sign. So the sub-expression there is phi 0 minus phi 2, and that appears in both phi twiddle 1 and phi twiddle 3. So if my job was just to compute this object here efficiently, then I could save as a little temporary variable phi 0 plus phi 2 and phi 0 minus phi 2, and I could recycle, reuse that information in 2 places, saving myself a little bit of arithmetic. And then, so those are the green boxes. Now, of course, if I look at phi 1 and phi 3, now it's just a tiny little bit harder to spot, but the same pattern emerges. You see it in the top line in phi twiddle 0, I have phi 1 plus phi 3. And in phi twiddle 2, I have minus phi 1 minus phi 3. And that's obviously proportional to that same there's a common sub-expression there, which is phi 1 plus phi 3, but in the top line it's added, and in the bottom line it appears with the relative minus sign. But nevertheless, it's a common sub-expression again. So again, I could use the same trick. And then in terms of phi twiddle 1 and phi twiddle 3, you see the same thing happens again, and it's perhaps even more obscured. I have I times phi 1 minus I times phi 3. And then in phi twiddle 3, I have minus I phi 1 plus I phi 3. And again, you see the common sub-expression is phi 1 minus phi 3. In the first line, in phi twiddle 1, it appears multiplied by I. And in phi twiddle 3, it appears multiplied by minus I. So those are written across in the right-hand column there are my 4 sub-expressions, my 4 sort of temporary variables that I could compute as a first step, and recycle, saving myself floating point operations if my task was just to compute these 4 Fourier modes from this 4 sets of data. And in there, I've got these little factors of I and minus 1 that complicate the sort of piece on the right-hand side, where I have the odd numbers appearing 1 and 3, and the even numbers appear quite straightforwardly in those 2 expressions. And of course, what are those expressions there? Well, you can see, of course, phi 0 plus phi 2 and phi 0 minus phi 2, they're the Fourier transform of those 2 numbers. If I had a little length 2 array, if I was to solve the even simpler problem, its Fourier modes are just the sum and the difference between those numbers. So the sub-expressions are actually Fourier transforms themselves of a half set, the even entries in that original array, phi 0 and phi 2, if I Fourier transform, I get those sub-expressions there. And also the odd section, phi 1 and phi 3. So those linear combinations there are the Fourier transform of those 2 numbers. So the sub-expressions, these little temporary variables that I would introduce to speed up my code that was evaluating this expression, are themselves Fourier transforms. So Fourier transforms of the even bits of the original array and the odd bits. And that's encoded in this Danielson-Lanczos lemma. So that generalizes to longer arrays, of course. So going back to my expression for the Fourier transform, I can write it as a set of 2 pieces. Well, again, just think back to that previous slide, where one piece is the Fourier transform of all the even entries in the array picked out, so skipping 2 strides along the array as I move along. So that's an array of length n over 2. So I can Fourier transform this problem, which is half as long, compute its Fourier modes, and then added in is the odd piece, but there's this extra little thing which is gets called twiddle factor here. This little phase factor appears in this expression. Put it here. There it is. There's this little extra phase factor that appears waiting in front of the odd piece, but nevertheless that's fairly easy to combine and add in. And again, in the previous slide, those phase factors were the extra little factors of I and minus I and plus and minus 1 that we needed when we were looking at the sub-expressions involving phi 1 and phi 2. So what are these 2 pieces here then? They're just written out. You see that they are then Fourier transforms. I think I'm missing some factors of 1 over n, square root n, and so on. So apologies for that. I think there's a typo there, just missing some trivial weighting factors. And they're the Fourier transforms over the data set that I take by pulling out every other bit of entry from my original set. So and that expression is easy to see. You can just see that basically by taking the original expression, break it into 2 pieces. taking the original sum and writing out the even terms in the sum and the odd terms in the sum. That's what you get for those two expressions. You tidy up your choice of indices and so on. So that's quite a straightforward result to see. But of course, it's a powerful one. Because also, yeah, and of course, it would generalize if I had an array that was some multiple of 3. I could write a slightly longer series, but nevertheless, I can generalize this to a sum of 3 pieces and so on. If I have a length 30 array, I could write this as a sum of 3 Fourier transforms, each of length 10. So this trick would work out just get more complicated Twiddle factors coming in there. So the trick generalizes to breaking the problem into other multiples. So instead of going from a length n array to a length n over 2 array, I could go from a length n array to a length n over 3 array, and I'd end up with 3 terms. So you can see how this recursion generalizes to more generally to arrays of different lengths. And so now this very nice, quite simple observation suggests a good algorithm now for evaluating the Fourier transform. So if I want to evaluate the length n Fourier transform, what I first do is I break the problem into 2 pieces, and I evaluate the length n over 2 Fourier transform twice, so it's 2 even and odd components. And of course, how do I do that? Well, I do that by breaking that n over 2 problem into 2 smaller chunks, the even and odd components of those subarrays, and all the way down until eventually I get to 2 numbers. Again, I'm assuming here that n is some power of 2. So I can generate a recursion. And my recursion is going to be, in order to compute the Fourier transform, first compute these 2 subtransforms. And to compute the subtransforms, I compute some sub-subtransforms, so I keep breaking down the problem into smaller and smaller pieces. I'm pretty happy with that so far. Yeah, good. Okay, so now I want to write a computer program to do this. And the first thing you notice is, as soon as you start thinking about doing this, the data is in its original format is not located in a very convenient way for a simple bit of code to be written. If you actually try to translate this into code, you want to know, thinking in a very sort of C kind of way, you think of an array just as a pointer at the start of a chunk of memory where your block of data has been written sequentially. And here that's not true. You're going to have to jump around at the very end with awkward strides, jumping around memory in sort of a complicated way to apply your recursion. So the code's going to get very messy very quickly. So there's a neat trick, which you can see explained in numerical recipes, for example, which is as a first step, before you even try to do any arithmetic, before you try and do this recursion, is just to shuffle your data into a handier format. And this trick gets sort of especially important when we think about an NP-harding code as well. And nevertheless, it's useful even if you're writing a serial code. So let's, as a first step, take our data, do no arithmetic at all. Let's take our array that we're trying to construct the Fourier series for, the Fourier transform of, sorry, and let's just shuffle it, move the data around in everything. No arithmetic here at all. No multiplications or additions. We're just shuffling data. I want to shuffle it into a format where this recursion applies more naturally. And so this is it done for a length 8 array here, just again to keep things nice and simple, but the idea generalizes. So here's the original array, obviously phi 0 to phi 7, sitting in my computer's memory, one next to the other, sequentially. And after this shuffling, I want it in this order written out at the bottom, which looks a bit strange, but if you look at it, you see it's basically what we need for this recursion to apply effectively. And you see that on the left-hand first 4 slots in my computer's memory after I've done this shuffling are all the even entries. 0, 2, 4, and 6 are all in there. They're still shuffled around a bit. But the even numbers appear first, and the odd numbers appear at the end.
Thank you very much.
And then if you look even more closely, you see that the first two numbers are the entries whose indices mod 4 are equal to 0. And those are going to be the bits of data that we'll need to when we get down to the second level of recursion. So we want to go from this top sequence down to this lower sequence, and I claim that this is going to be a much more convenient way to lay the data out in order to apply this recursion efficiently. And of course, the data locality, changing the data locality, hopefully that will improve the performance of our code if we think about caching and so on as well. We're not just helping ourselves in terms of writing the code more straightforwardly, we're also hopefully helping the memory management system find the data as we need it to construct each of these steps. And the recipe is basically to write out the indices of this array in binary. Now, of course, I've made this assumption that the array has length 2 to some power. Here, the power is obviously 3, so I can represent all of the addresses of these elements in this array as 3-digit binary numbers. So there they are written out. And the shuffling recipe is basically take each one of those numbers written in binary and write them backwards. So 0, 0, 0 goes to itself. I see 0, 0, 1, 1 goes to 1, 0, 0, and vice versa. So it's an exchange. And basically then swap those two entries around in the array. So entry 1 and entry 4 get switched around because entry 1 is 4 written backwards in this 3-bit addressing language. And you see, of course, there are some palindromes in there, 111, 101, 010. They're palindromes, they just get left alone. And there's some numbers which get moved around. And so then we end up with our original array getting shuffled into this bottom array. Yeah, so I mean, this is a permutation, and of course it's one which is it's an involution as well. If I do this twice, I get back to where it was. So it's a good way to test your code. It is only inverse. And now I'm ready to do the Fourier transform. Now the data is in a much handier ordering for this Danielson-Lanczos lemma to give us a very handy recursion. And so now we get to work. So the recursion defines the length 8 Fourier transform in terms of two length 4 Fourier transforms, which we can then iteratively apply that recursion relation and say that a length 4 Fourier transform can be written in terms of two length 2 Fourier transforms. And so you can see that that's where we have to start. We have to start first by evaluating those very short transforms. Then with those transforms, those length 2 transforms done, we can construct the length 4 transforms, and then finally come back up to the top of the tree, if you like, and evaluate the final answer, the length 8 transform. So the first thing we have to do is construct these length 2 transforms. And now you see that's where we get these butterfly patterns, as they're called, maybe obvious reasons. And inside in data, what we do is we call a little length 2 transform code 4 times. And what that does is, first of all, it constructs the Fourier transform of phi 0 and phi 4, which means adding and subtracting those numbers, and they will overwrite the bit of memory that's storing those numbers. So we're going to overwrite the array. So it's a nice algorithm in terms of memory usage. Its memory footprint is small as well. As the recursion proceeds, we don't need to pile up more storage. We're just going to overwrite the array as we go along. We never need to refer to phi 0 on its own again in this sequence. We only ever use those two temporaries, phi 0 plus phi 4 or phi 0 minus phi 4. So we can overwrite the array. So the first step, we're going to add and subtract phi 0 and phi 4, which are sitting next to each other in memory. That's nice. And overwrite those two pieces of memory with those two values. And then we're going to do the same thing for phi 2 and phi 6 and so on, all the way along. And now you see why this reordering of the data is so handy, because you can just imagine writing a function now where you just need to pass a single pointer, which is basically the location in memory of this little pair of numbers, this length 2 array, and you just work your way down the array, and don't have to worry about finding the data in some complicated way. The data is contiguous. So after this first step, then I've overwritten those 2 entries there with phi 0 plus phi 4 and phi 0 minus phi 4. Maybe I can write this out just to see the steps. So as a first step, where the first butterfly applies, phi 0 plus phi 4, phi 0 minus phi 4, and those 2 entries. And this minus sign here is this little twiddle factor here, which applies on this right-hand leg. It's just -1. Space factor that appears in the Danielson-Lanczos. And I work my way along. So here in this array entry, I have phi 2 plus phi 6, phi 2 minus phi 6, and so on. And I overwrite. And then in the next step of the recursion, I'm going to do a length 4 transform, but now I'm going to express it just as a sum of these. The Danielson-Lanczos lemma tells you to express it as a sum of these with various twiddle factors of the 2 components of the length 2 transform, which I've evaluated here. So in the next step, I can combine these entries here. Now with the twiddle factor is going to be and again, you think of this little twiddle factor living on this right-hand leg of the tip of the butterfly's wing, if you like. So what do I get? So I'm adding these 2 things. I get phi 0 plus phi 2 plus phi 4 plus phi 6. Here I'm going to get phi 0 plus phi 2 plus phi 4 plus phi 6. And I apply the same recipe here. With these pairs of data. So that's one application of this Danielson-Lanczos lemma to say these 2 components I can get from adding these 2 components of the length, which are part of the length 4 Fourier transform, I can get by combining 2 length 2 Fourier transform components. So now what's sitting in this box? Phi 0 plus I phi 2 minus phi 4 minus I phi 6 phi 0. That's what goes in that box. That's right, isn't it? Okay. Just add these 2. That's also right on here. Phi 0 plus I. And again, the trick is that I will overwrite. So I never need to refer to this number, whatever it is, on its own again. So I overwrite that memory location. And then finally, the Danielson-Lanczos lemma again tells me to construct the length 8 transform in terms of a sum of pairs of pieces of the length 4 transform. So again, you have 4 butterflies at the end, in the last entry, with the appropriate twiddle factors now, which is going to be the 8th root of unity. Again, sitting on the right-hand side. And eventually then what we'll end up with, and you can see how the trick works, some more data coming over here, which will be combined with the last twiddle factor, which is the hopefully the right one, and we end up with the right answer, with the entry in the first three components of his, just adding phi 0, phi 1, phi 2, could add it together. So you can just work through the last step if you want to just see how that works out, but it's following the same recipe. And again, we'll be overwriting the array. And so at the very end, we'll have the full answer. And now you see why the algorithm is n log n. Basically, at each horizontal stripe there, the operations that I need to apply those butterflies, they're just sort of multiplications, additions, and subtractions of pairs of numbers. And so there's just n butterflies written out horizontally on each stripe. So there's order n operations. Each butterfly operation takes of order 1 operations. It's just additions and subtractions, and it's taking pairs of numbers and adding and subtracting them. And you see, if you look horizontally and count the number of butterflies at each level, each stage, you see there's 4, 4, 4. It's constant and proportional to the length of the array. So it's n of the 2 here. So that means that the algorithm scales proportional to n times the number of the depth of these recursions, the number of times I have to apply this recursive factorization, the Danielson-Lanzos lemma, breaks apart the array in factors of 2. And of course, if my array is length 2 to the k, the number of times I need to chop it, divide it into two pieces, is just k. And a k then is, of course, the logarithm, base 2 logarithm of the array length, n. So the total amount of work, which is just basically the number of butterflies inside this picture, is proportional to n, that's the horizontal counting, times k, which is log n. So we have an n log n algorithm. So rather than evaluating this transform into n squared operations, we reduce it to n log n, which is, like I say, a huge saving. Okay, so now let's think how we might parameterize this. And here's where the fun kicks off. And so, I mean, if we just think about this now, let's imagine we have, let's just start with 2 MPI processes, and we have a data parallel array, so that the first 4 numbers are sitting on our first MPI process, and the second half of the array is sitting on the process 1, rank 1. Oops. So the first thing, of course, what I haven't discussed yet is how we're going to do the shuffling. That's the sort of hard part. But now you see what's nice is, of course, the first 2 iterations in this sequence here, if I look at these butterfly patterns, if I've done the shuffling and I have broken this array in a data parallel way so that one process has those first 4 numbers, the even bits of the original data set, and the second MPI process has the odd bits, you see that in the length 2 and length 4, the first pair of recursions, there's no, none of these butterfly lines cross that boundary, sort of imaginary boundary that sits between the middle of these 2 parts of the array. So there's no point where at which process 0 needs to talk to process 1 to get to fetch some data. The first 2 steps. And it's only at the very end where there has to be some communication happening. So you see again this bit reversal trick, we haven't done it. So it's been done here, but I haven't explained how we're going to do it. That's the first thing. Localizes the data in a very nice way, which is especially suited for MPI codes. You see that we've shuffled the data in this way such that each MPI process can maximize the amount of work it does locally, it can maximize the number of these iterations, so it can go down this recursive call before it has to start sending again. So you see this reversal trick is not just a nice bookkeeping trick that's very handy to tidy up your serial code. It gets almost crucial now when we think about an MPI implementation, to really cut down on communication. And this shuffling has really put the data in a format such that the amount of communication is minimized. The amount of work that I can do, the number of steps I can go down this recursion before I have to start sending and receiving data again is maximized. And you see that again with this butterfly pattern. There's a nice big gap, sort of canyon down the middle of my slide there, where process 0 and process 1 don't have to talk to each other at all. And obviously now if I had 4 MPI processes, it's not quite so nice, but still the first step, again, there's a gap in between phi 0 and phi 4, and phi 2 and phi 6. So if those two numbers were on an MPI core process, and 2 and 6 are on a separate one, again, this useful work that can be done before we have to start communicating. So again, this bit reversal trick really maximizes data locality in a way that it makes an MPI code as efficient as possible. And you can obviously compute how much communication and how many of those recursions you can do before you have to start communicating. It obviously depends on the number of MPI cores you have and the length of your array. So every see that trick, just basically just exploiting the sort of gaps in between these butterflies, which has arisen because I've done this reshuffling. So then the task is, okay, the start point here is has been reshuffled. So before I have this nice feature, I've obviously got to take my data, which is data parallel, sitting on lots of MPI cores, and I've got to reorder it, and that again, that's going to involve communication. So you see why this is a code that you don't want to have to write yourself. Basically, you've got communications, first of all, to get the data into just before you even start doing any floating point, just to get the data in a useful format, which is that top line, which is this bit reversal reshuffling. You have to write some nasty bookkeeping code that reshuffles these things. And then when you start actually applying the dimensional Landslash lemma, which is in this picture here, well, you've improved data locality, so it's going to run fast, but now, of course, you've still got to do more communications later on. You've got to send the data backwards and forwards to construct the final answer as well. So it's an ugly thing to have to write. Okay, so how are we going to write? Let's imagine writing an MPI implementation of just that first piece. So I'm not going to do any arithmetic, let's just do data shuffling. It turns out with a little bit of work and a little bit of thought, you can actually do all of that bit reversal trickery with a single MPI core, which is quite a nice feature. And putting aside all the initialization stuff, obviously. But in terms of the function that actually does the shuffling, there can be a single MPI function called in there. So that's rather nice. But unfortunately, it's an expensive call in the sense that it's the all-to-all MPI call, which, again, asks every process to send to every other process. So you have to hope that the engineer of the HPC system that you're running on has done a good job of optimizing that particular, optimally hard almost MPI task. Nevertheless, you can do it in a single one. That's not, of course, necessarily the most efficient way of doing it. Perhaps MPI all-to-all might be hideously inefficient on the system you're running on. Okay, how does that work? How can I do that? How can I achieve that objective of basically making a single MPI call, pushing all the hard work onto the engineer, software engineer who has to write in the MPI on the system I'm going to run? Well, let's imagine this now for a situation where we have an array that's a bit longer. Let's take a 128 element array. So I need 7 bits to store an address in that space. And let's put it over 4 MPI processes. And in this construction here, I'm going to assume that basically the number of numbers stored on an MPI core is larger than the number of MPI cores. So I'm going to break a global address, which in this sense is sort of, in this abstract sense, is this 7-bit number, into 2 pieces. And this is what you get if you basically data parallelized in the obvious way your original array, where you basically took the first chunk of the array, the first, 32 numbers, and gave them to process 0, the next 32 numbers, and gave them to process 1, and so on. Then the global index, where is array entry 72, you could figure out by writing the number 72 in binary, and it would be located on process, well, whatever it is, the index of the process you get from the most significant 2 bits of that number. And the memory address on that MPI process would be the least significant 5 bits. So you can think of taking a 7-bit sort of abstract global address and breaking it into its MPI part, which is the first bit, and its local part, which is the lower, the least significant. And of course, our objective is to take that memory address, whatever it is, written out in this binary representation. Each one of these A's is just a binary digit. And globally, again, thinking conceptually about what we're trying to do, we're trying to bit reverse that thing to optimize this data locality trick that we have. So we want to go from A6, A5, A4, 3 to blah, 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 that address down to A0, 1, 2, 3, 4, 5, 6, where I just write it backwards. So how can we achieve that just with a single MPI call? And you can do it in basically 3 steps. The first step you have to do is sort of what I call a block shuffle here, which is basically take the most significant number of digits where the number now is the difference between 5 and 2. So that's three bits in this case here. So it's to think of it as sort of an abstract digit which can take values from 0 to 7 in this case, and now do a sort of a shuffling on that funny looking indexing system. Write the 7, the 8, the 3-bit part of the address, take that from the most significant part to the least significant part, and then shuffle the 2. Now you see what I'm doing in this addressing here is I'm not changing the most significant bits there, the MPI address. So I can think of this operation here, what I'm doing in this shuffling step can all happen locally. So there's no MPI calls in this first step. And there's I can see that because the A6, A5 digits here of the data, of that block of data that's getting shuffled in some complicated way on each MPI process, that hasn't changed. I've left that invariant. But I've shuffled the local part of those of the data in a way now that allows me to get those digits, transmit those digits in an appropriate way using an MPI call. So the next step is to call this MPI all-to-all function. And that basically sort of transposes the MPI index. You can think of it in this sort of abstract address space, so global address space. It transposes the MPI indices with the top 2 local memory address bits. And the number that get transposed is the same. So 2 bits, if I have a 2-bit MPI address, which I would need for a, if I have 4 processes, 2 bits get shuffled with the 2 bits at the top. And what MPI all-to-all does is it basically takes an array. If I have 4 MPI processes, it slices that array up into 4 pieces and sends the first piece to process 0, second piece to process 1, and so on. So it's doing quite a sort of conceptually simple thing, but written in terms of this addressing language, you see it's just interchanging those bits in this address space. So that middle step there is an MPI call, and it can be done in a single step, MPI all-to-all. Now, whether it's done efficiently depends on the machine you're running on, of course. But I'm not quite done. You can see that once we've made that transposition step, I have the right bits for the leading to the MPI process, so the data's found its way to the appropriate MPI process, but it's still backwards in terms of its local addressing. So I still need to do some more shuffling. And in fact, that's just basically what I can basically recycle my old bit of serial code that I wrote to do the bit reversal. You see now I just need to write that local address in a bit reversal way. So I need to do basically what we were describing a few slides ago and reorder the array at that point. So I just write this little lowest, the least significant 5 binary digits backwards using my bit reversal trick. And you see 65432 goes to 23456, and now I have an address. Once I've performed these 3 operations, I should have an array, a data parallel array that's distributed across these MPI cores, which is bit reversed, which is what I need now for for my butterfly recursion pattern. So now I've got the data in this example here. I obviously only have 8 numbers. It's a short array. Got the data in this optimally localized format now, so that all the arithmetic can be done as locally as possible. And it requires a few MPI calls. That's really so everybody happy with that? So you can see now I can. So the upper and the lower steps there, which are local operations, are not the same. That's an important point. They're not identical operations. They're doing different things. They would be identical, I think, if the length of the data locally and globally is the same. Yeah, so A2 is length 0. And so, but in general, it's a more general case here where the local address is different from the number of MPI calls, the length of the array is different from the number of MPI processes we have in our machine. Then in general, the top operation and the bottom operation are different. So as advertised, well, okay, oh yeah, I'm going to look at this. Quick look at it just to see. It's not an impossibly difficult piece of MPI code to write. I'll post this online so you can take a look at it. This is my attempt at it, and it's not so hideously difficult. It's probably impossible to see, isn't it? So here's, I'll post this online so you can take a look at it, see if you can test it as well. I haven't tested it very carefully. You can see if you agree that it's doing what I just advertised. But the sort of key point is that the only MPI call that I make is this all-to-all operation step here. So very, you can encode it fairly neatly in the MPI environment. So I'll stick that up online so you can take a look and see if we can reproduce the logic that I've just shown you there. But just to finish up, let me very quickly spend 2 minutes showing you the sort of a library use, just to show you that these libraries are very easy to implement, really. Very nicely written so that you can use Fourier transforms in your code. You can plug these library functions in quite straightforwardly. Let me just very quickly show you one of the sort of leading libraries, that's the most widely used libraries, and that's this FFTW, the fastest Fourier transform in the West. I think it originally stood for, they might have backed away from calling it that anymore. And FFTW is sort of quite famous library for this, and it's really highly optimized. They've taken account of all of these problems that we've discussed. You're not forced to use arrays that are some power of 2. That it allows you to use arbitrary lengths, and what it does is it tries its best to find a recipe that will do your transform efficiently. So it tries to factorize the length of the array in a very as an efficient way as it can, and also tries to organize which length Danielson-Lanczos lemmas it uses to break the data apart. It shuffles those around, and then actually, if you really want to use it in sort of expert mode, if you like, you can actually have it do some different numerical experiments and figure out which of those particular orderings is fastest. So it's very fancy, very nicely written, very flexible and efficient package to use, and with an interface that's reasonably straightforward. So it's worth just, as a little exercise, I'll post this online as well. You can mess around with this and just see how it works, and there's lots of reference material online if you want to see how you would plug this library into a piece of code that you were writing. And it works, like I say, by you define these plans, as they're called, and that's where it tries to store information about what's the best way of actually carrying out the problem that you're interested in. If I would, in this example here, this is a 2x2 array, 256 by 256. So it's doing the 2-dimensional Fourier transform, so it generalizes just to one-dimensional transforms we'll be looking at. You can get it to construct this thing which is called a plan by an appropriate function call saying what you want to do. And at this first step, it basically, depending on what parameters you give the code, it goes away and either guesses what's going to be the most efficient recursion to construct. If it was a length 6 array, do I use the sort of length 3 Danielson-Landstrauss recursion before the length 2 or 2 then 3? Which order? Because I can factorize in any order, and I can construct a recursion in any order. And it tries to figure out, given the factorization of the length of the array, which order of those multiples is the best one to implement. And like I said, you can even switch on a flag that allows you to let the code experiment before it.
Yeah, correct. Just in the function call, it's mentioned. Yeah, the DFT is mentioned, so direct Fourier transform, which would be not an FFT, would it? Because I thought there were two different things.
Or if I put this is wrong with code, if I posted it. I can't remember what that bit means now. I have to look that up. Yeah, yeah.
Just
You're an expert. Yeah. Let me check that. Actually, that's a good point. I thought that was the you can do cosine and sine transforms as well, and I thought that was the complex. It's just referring to the fact that I want both components and not constrain them anyway. I should check that. I check that. Yeah, okay, I check that. So then you construct this plan, which sort of contains pointers to the memory locations and so on. You set it up, and you can send a flag, which, like I say, allows the software to experiment with the optimal breakdown. And then when you actually want to do the transform, you just do the FFTW, execute the plan. So again, you see the actual Fourier transform, the interface that you end up writing into your code that's doing the science bit is very straightforward once you set up this plan. So it's a very nice interface for you to use. Okay, good. Yeah, I'll check what that DFT thing means. I thought it was. Okay, I'm confusing myself. I should actually check. Okay, good. I think we're sort of out of time there. Maybe next week we'll look at some examples of a bit of code where we might use the Fourier transform in action, sort of thing. So it obviously has lots of applications. The Fourier transform is useful for all sorts of science applications. Convolutions are a big one, obviously, and sort of Fourier acceleration of solvers for partial differential equations. You can solve the diffusion equation directly in Fourier space and lots of other differential equations, but you can accelerate more complicated differential equations where there isn't an analytic solution in Fourier space, can still be accelerated. It's the natural basis for any physical system that's translation invariant. So it has many applications in numerical computing as well. So let's perhaps look at one of those very quickly next week. Okay, good. We'll finish up there. I'll put that code up online and I'll try and answer your question. How did everybody get on with the Schur sequence? Yes, sorry, Stern sequence. I'll post my solution up online as well, so you can take a look and see how much nicer your version is than mine. And, obviously, if anybody's any questions about that, then you can feel free to track me down. I'll let you know. So I'll give you another little homework for tomorrow's session. But this afternoon, I think Tony's hopefully going to talk to you a little bit about your leapfrog homework. So back in the lab at 3:30ish, and have a go at see if you can construct some nice leapfrog integrators in code as well, and see if you can construct a shadow Hamiltonian and a force gradient. Okay, see, you know where we're going. Hopefully, the same lab as we were in yesterday.
It's confusing when you refer to these.
Yes, I know.
Yeah.
Not density functional theorem. No, no. Different DFT. It's doing.
The decomposition is as would be usually be, so turn it off. But the actual Fourier transform is FFT.
So it's basically the transform itself, the first slide that you showed, that's DFT. But the method that we apply to compute the end function is fast Fourier transform. So it's basically computing a discrete Fourier transform.
Right.
Fast Fourier would be fast Fourier transform would be the actual computation, the fact that you divide the const and the
Yeah. Oh, that's the. Oh, it's when it does that reshuffling.
yes.
Yeah. Okay. Oh, right. So DFT does the reshuffling and then does the Danielson-Landschuss stuff. FFT would not do the reshuffling, would just do the Danielson-Landschuss stuff. Is that right? Do I understand that right?
DFT would do it completely.
Yeah. It does it
directly,
yeah.
And it would be organized.
Oh, really?
Or it's just a mathematical.
Oh, okay.
Yeah, so it's the
Oh.
equivalent of the continuous Fourier transform.
Okay. Okay. Oh, I was
I think that the fast Fourier transform just refers to the fact that it's computed in n log n. So it's
Yeah,
a
yeah,
faster
yeah,
way
yeah.
to compute the discrete Fourier
Yeah, sure. I didn't know they even implemented the naive algorithm. Okay. Oh, I'll go and check that. All right. Oh, thanks. Good. All right, thanks. Okay, see you in half past. Yeah.
transform. I don't think I'm going anywhere. So the stage is half an hour.
See you in a bit.
It'll be too much. Yeah, that's the amount of projects.
Yeah, there's definitely